All right, let's dive right into this. Today, we're exploring how artificial intelligence solves massive, mind boggling puzzles. We're talking puzzles with literally billions of moving parts. Welcome to This Explainer. We're going to look at some of the absolute most fascinating problem solving techniques in computer science and see exactly how machines tackle these incredibly complex environments where the sheer number of possibilities would, well, it completely break an ordinary computer.
So imagine for a second trying to find a perfect solution when checking every single possible path is literally impossible. Seriously, if you tried to map out every single move in a complex game, or say a massive logistical network, the universe would literally end before your computer finished calculating the whole shebang. So, how do algorithms actually navigate environments like this? How on earth do they find a needle in a haystack the size of a planet? To kind of anchor this whole concept, we're going to look at the classic 8 queens puzzle. The goal here is simple, but the execution, actually, it's a really tricky. You just have to place 8 queens on a standard chessboard so that none of them can attack each other. Now, trying to randomly guess this layout is a complete computational nightmare, which actually makes it the perfect training ground for AI. All right, here's our roadmap for this explainer. First, we'll cover the optimization puzzle, then local search and n-queens, moving on to the hill climbing trap, the simulated annealing solution, and finally, beam and genetic searches. Let's kick things off with section 1, the optimization puzzle.
Now, in optimization problems, the AI absolutely does not care how it gets to the end. The path? Totally irrelevant. It's kind of like a traveling salesperson trying to find the shortest route between 20 cities. The history of how you planned that route doesn't matter at all. The only thing that actually matters is that final optimal configuration. The goal state itself is the solution.
Moving on to section 2, local search and n-queens. So, if the path doesn't matter, local search algorithms just look at their immediate neighbors. They keep a single, current state, and they just try to iteratively improve it. And the huge advantage here is that this takes up almost zero memory and it's incredibly fast. But there's a catch, right? Because it's a bit short-sighted, the AI might completely miss the area of the board where the actual perfect solution is hiding out.
To figure out how it's doing, the AI measures its progress using a heuristic cost function. We just call it H. Here, H is simply the number of queens attacking each other. Starting with a totally messy, high-scoring board, the AI's only job is to look at its immediate options and make a single move that lowers that number. It just keeps sliding pieces around, aiming for that perfect global minimum where H hits exactly 0.
Which brings us to section 3, the hill climbing trap. But okay, here is the trap. The AI can get completely stuck in what we call a local minimum. Imagine the board is almost perfect, right? Our H is down to just 1. But from this specific position, every single possible move the AI can make actually increases the AI value. It makes things worse. And because a basic local search is hardwired to only ever step toward a better score, it just stops searching. It thinks it's done, but it actually failed. The source material uses this incredible metaphor to describe this trap. It says it's like climbing Mount Everest in thick fog. Imagine you're climbing this massive mountain, but you can't see anything around you. You only know if your very next step is tilted up or down. So if you happen to reach a small flat shoulder on the side of the mountain, every step around you goes down. Relying purely on that local feedback, you stop thinking, hey, I've reached the absolute peak of Everest, when really, you are miles away from the true summit. To combat this fog, AI uses some clever, kind of brute force variants to escape these false peaks. It might choose randomly among the uphill moves, or just generate random options until it finds a better one. But the most extreme method? That's a random restart. Basically, if it gets stuck, it simply teleports to a completely random new starting position on the mountain and climbs again until it hits the actual summit.
Next up, section 4, the simulated annealing solution. So when brute force isn't enough, computer science borrows a brilliantly counterintuitive trick from physics. In metallurgy, there's a process called annealing. To make metals or glass incredibly strong, you don't just freeze them. No, you heat them up to a very high temperature, and then you gradually, carefully cool them down. This highly active, heated state allows the atoms to bounce around and eventually settle into their absolute strongest, lowest energy configuration. And translating this physical process into code gives us simulated annealing. The AI is literally programmed with a temperature variable. When the search begins, the temperature is hot, and the AI is actually encouraged to intentionally make bad downhill moves.
it willfully makes the board worse. Why on earth would it do that? Well, because walking down into a valley is sometimes the only way to escape a fake peak. As the search goes on, the algorithm gradually cools down, slowly reducing those bad moves until it zeroes in on the true solution. It's pretty amazing.
And finally, Section 5, Beam and Genetic Searches.
Enter the beam search. So instead of dropping a single climber onto the mountain in the fog, beam search drops an entire team, represented by the variable k. All these randomly generated states start exploring at the same time. But rather than letting them all just wander blindly, the algorithm looks at all of their next steps and only keeps the k absolute best ones, discarding the rest. It's a highly efficient way to share knowledge across a whole set of simultaneous searches. This ensures the algorithm focuses its computing power only on the most promising paths.
And if borrowing from physics wasn't enough, AI also borrows from biology. With genetic algorithms, we don't just tweak one layout. We evaluate our team of climbers, pick the ones making the best progress, and we literally combine them. Successor states are generated by mating two successful parent states together to breeding new, theoretically superior offspring. It's literally digital evolution in action. It combines the best traits of different solutions to leapfrog over those local minimum traps entirely.
So by combining simple local searches with the physical cooling properties of metals and even the biological evolution of genes, algorithms can solve puzzles that would take standard computers trillions of years to crack. It's a real game changer. And it really leaves us wondering, as our digital environments become even more incredibly complex, exactly what other natural processes will we soon borrow to help our machines see through the fog? Thank you so much for joining me for this explainer. I really hope it gave you a whole new perspective on how machines actually think. Keep exploring, and I'll catch you next time.